In this video, I'll be discussing the applications of calculus in supply and demand. I'll be discussing the topics of consumer surplus, price elasticity, income elasticity, taxes, and tariffs. In the AP Macroeconomics curriculum, we deal exclusively with linear functions of supply and demand. In that case, the consumer surplus is simply the area of a triangle, which you can see shaded in on the image on the left. Regardless of whether or not the supply and demand curves are linear, consumer surplus can be calculated as the area under the demand curve and above the equilibrium price. To find the consumer surplus for nonlinear supply and demand curves, the first step is to find the equilibrium quantity and price by setting the demand function equal to the supply. The next step is to integrate the area under the demand curve from 0 to the equilibrium quantity. It's important that the demand curve is in terms of quantity, meaning it takes quantity as its input. The final step is to subtract the area of the rectangle below the equilibrium price. In other words, integrate the function y equals the equilibrium price from 0 to the equilibrium quantity and subtract from the previous calculation. This results in the formula consumer surplus equals the integral of from 0 to the equilibrium quantity of the demand function minus the demand evaluated at the equilibrium quantity with respect to tau. In this case, the tau variable is simply representing quantity. However, I didn't want it to be confusing using equilibrium quantity as the upper bound. Here's an example problem in which we'll calculate consumer surplus. In this case, the demand curve is modeled by the function 3 over the quantity demanded plus 1 squared minus 0.2. The supply curve is modeled by the function 0.5 times the quantity demanded squared. Setting the demand function equal to the supply function, we get an equilibrium quantity of 1.029 billion units. Evaluating the demand curve at the equilibrium quantity, we get a price of $0.529 billion. $0.529. Plugging these values into the formula we determined on the previous slide, we get a consumer surplus of $0.77 billion. The next topic I'll be discussing is called arc elasticity, which is the same thing as price elasticity of demand over an interval. In the AP Macroeconomics curriculum, this is topic 2.3, which we learn is price elasticity of demand. One thing that's important to note about arc elasticity is that it's measured over an observed change in the quantity demanded. The formula we learned in class was price elasticity of demand is the percentage change in the quantity demanded over the percentage change in price. Price elasticity of demand is often denoted using the Greek letter eta with a subscript of P for price. Rewriting the formula we learned in class, we get delta Q over the average Q value, so the change in quantity over the average quantity divided by change in price over the average price. It's important that we add a negative here to get the proper sign on our resulting elasticity coefficient. We can then rewrite this equation, and we get our final equation for price elasticity of demand: negative change in quantity over change in price times the average price over the average quantity. As you can see here, the change in price is the vertical distance between 2 points on the demand curve. The change in quantity is the horizontal distance between 2 points on the demand curve. To calculate the point elasticity, or the price elasticity of demand at a certain instance, we simply take the limit as delta P and delta Q approach 0. Taking the limit of the formula we got in the previous step, we get a new formula for the price elasticity of demand, this time at a specific point. That formula is price elasticity of demand equals negative derivative of quantity demanded with respect to price times the price over the quantity demanded. That same math and logic can be applied to the supply, and we can get a price elasticity of supply formula, which is negative derivative of supply with respect to price times the price over the supply. Here's an example problem for calculating the point elasticity at a certain point on the demand curve. In this case, we'll be using the point 4, 2.5. The demand curve is modeled by the function quantity demanded equals 10 over the price. This can be rearranged for price, and we get the equation price equals 10 over the quantity demanded. Taking the derivative of the quantity demanded with respect to price, we get negative 10 divided by p squared. Substituting in the value for p, in this case 2.5, we get the derivative of quantity demanded with respect to price is negative 1.6. Dividing price by quantity, we get 0.625. Substituting in these values into the formula we determined earlier, we get 1.6 times 0.625 equals 1. This negative 1.26 here should be a positive 1.26. It's worth noting that for any demand function of the form Q equals A P to the negative B power, the price elasticity of demand is equal to B, or the absolute value of the exponent. We previously found the equation for the price elasticity of demand using two variables. In reality, however, the quantity demanded is dependent on more factors than just price. Income and price together usually influence the quantity demanded. Because of that, the quantity demanded is a function of two variables. Here's an example function on the left. Because multiple variables are involved, partial differentiation should be used in place of ordinary differentiation. In that case, we would change the original formula to negative partial derivative of Q with respect to price times P over Q. To calculate the partial derivative of Q with respect to P, we would treat Y, or the income, as a constant, and we would differentiate as usual. Another way of thinking about the partial derivative of quantity with respect to price is to set the income equal to a constant value. As you can see on the image on the left, that would be this blue plane. The partial derivative of quantity with respect to price would then be the derivative of the curve, here it's in black, where the function and the plane intersect. Here's an example problem of price elasticity of demand with multiple variables. In this case, quantity demanded can be modeled as a function of price and income. The function used in this image on the left is Q equals 0.6 times price, or P, to the negative 0.4 times Y, or income, to the 0.9 power. To take the partial derivative of Q with respect to P, we simply hold Y, or income, constant, and then take the derivative as we normally would. The negative 0.4 power on the P variable simply comes out and gets multiplied by 0.6, and the Y stays as is. In other words, we simply get the partial derivative of Q with respect to P equals negative 0.24 times the price to the negative 1.4 power times the income to the 0.9 power. It's important to note that we subtract 1 due to the power rule in the price exponent. Substituting the values in to the formula we determined in the previous slide, we realize that the price and the income will both cancel, and we'll be left with this fraction of two numeric values, which are 0.24 and 0.26. Dividing the two, we get a price elasticity of demand of 0.4. Income elasticity is a measure of how sensitive how sensitive the quantity demanded is to changes in income. Considering only income and quantity, the income elasticity of demand can be found using the equation negative derivative of quantity demanded with respect to income times income over quantity demanded. As we found earlier, price usually influences quantity demanded as well. Therefore, the quantity is a function of two variables. Because of that, we have to use partial differentiation. The formula then becomes the income elasticity of demand equals negative partial derivative of quantity demanded with respect to income times income over quantity demanded. Just like we did before, to calculate the partial derivative of the quantity demanded with respect to income, we treat P, or price in this case, as a constant and differentiate as usual. Here's an example problem for income elasticity of demand with multiple variables. In this case, I'll be using the same function as I did before. This time we'll just be examining the income elasticity of demand. The function is quantity demanded as a function of price and income equals 0.6 times the price to the negative 0.4 power times the income to the 0.9 power. Evaluating the partial derivative of the quantity demanded with respect to the income by holding the price constant, we get negative 0.54 times price to the negative 0.4 power times income to the negative 0.1 power. Substituting in to the formula we determined previously, we get an income elasticity of demand in which the price and income will cancel, and we'll be left with 0.54 over 0.6, which leaves us with an income elasticity of demand of 0.9. Clearly, there's no calculus involved in calculating the tax revenue. However, for calculating deadweight loss, we will need calculus if the functions are not linear. In the macroeconomics curriculum, the deadweight loss is calculated as the area below the demand curve and above the supply curve from the quantity after the tax was applied to the equilibrium quantity before the tax. Writing this in terms of calculus, we get deadweight loss equals the integral of the quantity after the tax to the equilibrium quantity before the tax of the demand curve minus the supply curve with respect to the quantity demanded. Here's an example problem for calculating the deadweight loss from taxes. In this case, the demand curve is modeled by the equation 7 over the quantity demanded squared minus 0.1. The supply curve is modeled by the equation 0.1 times the quantity demanded squared. In this case, the per unit tax is $2. Setting the supply curve equal to the demand curve, we get an equilibrium quantity of 2.807 billion units. Setting the supply curve after the tax equal to the demand curve, we get a quantity after the tax of 1.71 billion units. Plugging these values into the formula we determined previously, we get a deadweight loss of $0.919 billion. In the AP Macroeconomics curriculum, deadweight loss is calculated by adding the area under the supply curve and above the world price from the quantity produced before the tariff to the quantity produced after the tariff, which is this first green triangle here on the left, and the area under the demand curve and above the world price from the quantity consumed after the tariff to the quantity consumed before the tariff, which is the second green triangle on the left. Writing this in terms of calculus, we have L for deadweight loss equals the integral of the quantity produced before the tariff to the quantity produced after the tariff of the supply curve minus the world price with respect to quantity demanded plus the integral of the quantity consumed after the tariff is applied to the quantity consumed before the tariff is applied of the demand curve minus the world price with respect to the quantity demanded. Thanks for watching. I hope you enjoyed this video.